for the introduction, and I'd like also to join the other speakers in thanking the organizers. It has been a very interesting week. I learned a lot, especially about surface acoustic waves and various other excitations. What? The matrix. I also learned about the printing press invention yesterday, which was actually very interesting, and I learned a lot. Okay, so in this talk, you will hopefully learn about the interaction between light and sound, and how to use light to imprint interesting, exceptional properties on sound propagation. And then I decided to add a second part to my talk, which deals with a very recent topic, which we are very excited about, that is interaction between light and magnons of the type that Yasunobu was already talking about. Now I want to start with the universe. This is one of the most violent events in the universe. You are looking at two black holes that are spiraling each other before they merge, and in doing so they will emit a very brief but intense burst of gravitational radiation. And it was only last September, as you know, that gravitational waves were first directly detected on Earth. So what you're looking at is the two signals that were detected at the two detectors in the US. You see this brief burst of radiation with frequency rising and then abruptly stopping when the black holes have merged. All of this happens on a very short time scale, 0.1 seconds, but the most amazing fact about this plot is the vertical axis, which shows the strength of the signal, which is only 10 to the minus 21 strain, that is relative change of length. And so how do you detect these very, very tiny changes? Well, these are the detectors that have been used. These are kilometer scale interferometers that are being used to detect the passage of gravitational wave. The idea, of course, being that if a gravitational wave comes along, it will change the relative arm lengths, and so you will get an interference signal in the output phase of the interferometer. And the way the interaction between light and sound or light and mechanical motion enters this story is, of course, that the reason why you get this length change of the interferometers is because the end mirrors are not just rigidly fixed to the ground, but they are free to move as the gravitational wave comes along. And you can ask yourself the question, how does the sensitivity of my device depend on the laser power? And it is in the answer to this question that actually radiation pressure forces first come into play. So if you look at the measurement noise as a function of the laser power, then at low laser powers it is quite obvious that you can improve the precision by increasing the power. This is simply because in a given time interval you just have more photons, and so you get a better signal to noise ratio. So the relative size of the shot noise of the laser beam is reduced as you increase the total laser power. But then as you increase the laser power even further, something interesting happens, namely the measurement noise becomes worse again. And the reason for this is really radiation forces. Namely, what happens here is that all the time you have a radiation pressure force acting on the end mirrors, and because even an ideal laser beam has Poissonian shot noise fluctuations of its intensity, these will give rise to force fluctuations that also act on the mirror and imprint a kind of jitter motion that masks the signal that you want to see. Now, at low laser powers, this effect is still very, very small and is completely overwhelmed by the other effect that you're just trying to measure your face sufficiently precisely. But at large laser powers, this is the dominant effect, which really sets your signal to noise ratio. That is the action of the fluctuating radiation pressure force on the end mirror. And somewhere in between, then there is an optimum, there is a sweet spot, and that's where you want to try to operate your gravitational wave detector at. So these structures here are the largest optomechanical devices on the planet. We are going to look at smaller scale devices, for example, living on the micron scale, and typically they look like this. You have an optical cavity that is driven by a laser, and just like in the gravitational wave detector, you have a movable end mirror. The idea being that as this mirror moves, the length of the cavity changes, and so the resonance frequencies shift. And since you're driving with a laser beam at a constant frequency, this shift of resonance automatically also means a shift of intensity. And this shift of intensity then in turn will change the force acting on the end mirror, so you have a true interplay between the mechanical motion and the radiation field. Now I want to write down the Hamiltonian for this device, and I will focus on the two most important degrees of freedom, which would be the mechanical mode, and out of the infinitely many normal modes, or almost infinitely many mechanical normal modes of the beam, I will pick just one and call its normal coordinate x. And then, in addition, there's the optical cavity, again, infinitely many normal modes. I will just pick one, the one that is driven by the laser, and I call the field operator A. So that would be the operator that annihilates a photon. So if I write down the energy, I will then say the energy is always h bar omega, the energy of a photon, times the number of photons, and the number of photons is A dagger A. Now, I already mentioned, however, that in this device, the frequency of the optical resonance, the frequency of a photon circulating inside the cavity, is no longer fixed, but it can be changed due to the mechanical motion. And the relative change of frequency is given by x over L. Yeah, so x, the displacement, divided by L, the length of the cavity. And so this is the important term that couples mechanical motion, x, to the light field in terms of the photon number A dagger A. And that is at the heart of everything that I'm going to talk about. So this is the optomechanical Hamiltonian. Then you would go on to add, for example, the fact that the mirror sits on this vibrating nanobeam, and you describe that also as a harmonic oscillator. So B dagger B would be the number of phonons, and capital omega would be the phonon frequency. Now, this looks relatively specific, but since about 10 years, there has been an explosion of interest in this field with many different experimental setups, such as truly mirrors being glued onto nanobeams, but you can also have light running around in a whispering gallery mode resonator. You can have light stored inside a photonic crystal mode. We will come back to that later. And instead of the light at optical frequencies, you can also have microwave frequencies. So you can have an LC circuit where the capacitor vibrates, and that in turn will change the LC frequency, and it's exactly the same physics again. So this is just to display more clearly where you find the radiation mode and where you find the mechanical motion. This is the standard Fabry-Perot setup that we discussed. You can also have a nanotube or membrane inside the optical cavity. This is the whispering gallery mode. That's the capacitor. You can have a cloud of atoms sitting inside the cavity and a photonic crystal device. Now, all these devices live typically on quite different length scales. For example, if you compare the photonic crystal against the torus, that's the true to scale. Okay, so people have been interested in this for various reasons. One of them is investigating fundamental physics, because the idea is you could use the light field to produce quantum superposition states of relatively massive mechanical objects, which would be far larger than what, for example, Marcus Arndt sends through his interferometers. And you could then use them to test hypothetical theories about extra decoherence sources that kick in at larger masses and that make our world classical again as you go to larger and larger scales. Now, another very important point in all of this is that mechanical motion, as we have seen during all this conference, is very versatile in that it couples to practically everything. So here we see how it couples to light or to microwave radiation. It can be made to couple to superconducting qubits or to spins or to cold atoms. And so you can use the mechanical motion as an interface between different quantum systems. Then there's the whole area of precision measurements. I showed the gravitational wave detection, which is probably the most precise measurement ever done on some scale. Also, people have really patented devices that use optomechanical effects to measure tiny accelerations on a chip. And then finally, if you scale down these devices and put them all on a chip, you can think about integrated circuits, where, for example, one part of the device would really measure something, another would be used for amplification, and so on, and you connect up these different parts. Now, I want to come back to the physics, and I want to talk about the simplest possible process that can go on in these devices. What you're seeing here is a typical situation. You are constantly illuminating the cavity with a stream of photons from a laser beam. But as you can see, most of them are reflected, and the reason is I have assumed the laser beam is not in resonance with the cavity frequency. They are red detuned, have a lower frequency. Nevertheless, let's assume there is already one photon sitting inside the cavity. And now what can happen, I claim, is that this one photon can be coherently converted into a single phonon that is a vibration in the nanobeam. Now you might protest that this does not fulfill energy conservation, but if you looked very closely, you see that while the photon is being converted into the phonon, something else happens, namely another photon appears outside the cavity. And so it's really a Raman scattering process where the blue higher energy photon gets turned into both a phonon and a red lower energy photon that then leaves the cavity. And it turns out that still, even though a photon leaves the cavity, the whole process is coherent simply because it joins the billions of photons inside this large laser beam. Okay, so on the theory level, the same process is best described in the following manner. You start from the optomechanical interaction, A dagger A times the displacement. And here I've already written the displacement in terms of phonon operators, so B plus B dagger. And then you realize that the coupling constant sitting in front of it is typically rather small. You can boost the effective coupling constant by just turning up the laser intensity. And the way to describe this is to say that the quantum field inside the cavity consists of two parts. One is the classical amplitude that is set by the laser drive, I call it alpha, plus some small quantum fluctuations around that classical amplitude. And now if you insert this representation into the original interaction and only keep the most important, the leading term, you end up with a quadratic Hamiltonian that always couples one photon operator, delta A, to one phonon operator B. So this is quadratic in contrast to the original interaction. In turn, in addition, something else has happened because you realize that now you multiply the bare coupling with this classical amplitude that is set by the laser drive. And that's now very, very important. We call this the laser-enhanced optomechanical coupling. Here G equals G0 times alpha. And not only do you boost the effect, and you can tune it now depending on the laser amplitude, but also the alpha appearing here really is the optical amplitude set by the laser, so it also has an optical phase. And that's very important. So you have a coupling between photons and phonons that also has a phase factor. Now, it turns out if you only have a single optical mode, you actually can get rid of this formally by a gauge transformation. But as soon as you have many optical modes, you cannot get rid of it anymore. And then it will become important. And so that will be an important part of the story. Okay. So this is the most important thing to take from this part of the talk. Good. So people have gone into the quantum regime. This was mentioned before. You can use the process that I just described to extract phonons out of the resonator and cool from large phonon numbers of thousands or millions down to the ground state of mechanical motion, that is to phonon numbers that are below 1. And then you can start to do quantum experiments. Now I want to end this introduction by bringing up this overview slide, which I once called the slopes of optomechanics because it was introduced at a winter school. The thing is color-coded in the same way that you would color-code ski slopes. So green means things that by now have become routine in the field and that the experimental groups are using as their toolbox, for example, the cooling that I talked about or the detection of mechanical displacement. Yellow is things that the best groups are currently working on, such as entangling mechanical motion and the radiation field, or wavelength conversion between microwaves and optics. We heard something about this previously at this conference. Red would be things that we hope can be produced in the next few years. And I'm specifically going to talk about optomechanical circuits where you couple many different optical and mechanical modes. And then black are obviously the things that we know it would be nice, and we have some ideas how it would work if only the coupling constants were much larger than they are today. Okay. Yes, please.
So you initially mentioned the, say, gravitational effect on the mechanical motion or mechanical coherence, right?
So there are two things. There's the gravitational wave detection, that's detecting the classical. You mean the fancy extra decoherence? Yes.
from that?
I think very fast. So there are two approaches. So it was originally suggested by people like Dirk Baumeister, and he's struggling towards this and using the lowest possible temperatures that he can use, getting adiabatic demagnetization. But this is still very far. The most promising approaches is probably the levitated spheres, where you get rid of any coupling to the substrate. So you reduce the standard sources of decoherence as much as possible. But even there, the true gravitationally induced decoherence is so many orders of magnitude away. So the point of view that people take is rather like some people in high energy physics are used to taking. Namely, you have some speculative theory which has some adjustable parameters, and then you do your measurements and you get new bounds, new upper bounds on the size of the effect. And then these upper bounds in the course of time will shrink and shrink and shrink. Yeah. Okay, so now let's couple many modes. So far I only talked about one optical mode coupled to one mechanical mode. This is already good enough to understand almost all quantum experiments in the field. For example, the laser cooling, displacement sensing, going into the strong coupling regime, where the coupling between the two modes is so strong that it overwhelms all the dissipation rates, so you can really see hybridized optical and mechanical modes. Nevertheless, it's obviously very interesting to inquire what would happen if you have many modes that you combine in such a way that it gives new functionality, because in principle they are always there, but you want to have new effects. For example, if you take two mechanical resonators inside a common optical mode, then you get an effective laser tunable interaction between the two mechanical resonators, even if they are relatively far apart and don't have any direct coupling. You can tune that by the laser amplitude and use this for state transfer or even entanglement generation between the two mechanical modes. Then if you have one mechanical mode coupled to two optical modes, this actually turns out to be the ideal setup to be able, in principle, to detect discrete phonon numbers inside the mechanical mode if the coupling were stronger than it is today. And then you can go on. For example, here, this is supposed to represent a circuit where you have modes wired up with waveguides, both acoustic and optical waveguides, or you can simply build periodical arrays. This is more for fundamental physics, mostly, where you study the quantum many-body dynamics of photons and phonons in such arrays. Now, this is, of course, all schematic. It's just yellow circles are mechanical modes and blue circles are optical modes. The question is, how can you implement this? And here's the largest optomechanical array that exists up to date, which stems from the group of Michael Lipson at Cornell. It involves 7 disk resonators that carry optical whispering gallery modes, and where the optics is evanescently coupled between the disks. In addition, these disks can vibrate, so you really have an optomechanical interaction. And their goal was to test an earlier prediction of ours about the synchronization dynamics of such mechanical resonators that are coupled via the light field. So this is on you see the scale bar, 20 micron or so scale. An even more flexible approach for the future might be photonic crystal structures. These were introduced into the field of optomechanics by Oscar Painter at Caltech. The idea is to have some freestanding slab of dielectric that is patterned periodically so as to give you a photonic crystal band structure. And then if you deliberately engineer a defect, for example, here inside the middle of the structure, the geometry is slightly changed, then you can get localized optical defect modes. We just heard an introduction to photonic crystals in the talk by Hubert Krenner previously. Now, in addition, because the whole structure is freestanding, it's also very good to have acoustic modes. And it turns out that the same structure where you have these snowflake-shaped holes is good to have a vibrational band structure. So you also have a phononic crystal at the same time, and you get localized phononic modes also at this spot. And that's now very good because they are so tightly confined on the scale of an optical wavelength that the coupling constants simply are very large. And in addition, everything is so small that you can now easily think about extending these devices, where here you only have one optical and one mechanical mode, to larger arrays. And that's what I want to talk about. So here is just an arrangement that you could produce. starting from such an optomechanical crystal, but now placing many such defects, each of which carries optical and mechanical modes. And they are, of course, coupled to each other simply, for example, by the evanescent coupling between one photon field leaking into the neighboring side. Yes, please.
Sorry, can you, just a naive person, can you give an intuition what makes these snowflakes so special?
Yeah, okay. So if you only wanted a photonic crystal, you could simply have holes. We have seen a lot of holes previously. The idea for snowflakes is to also have a nice phononic crystal. And if you look at it, focus on these triangles. You see these triangles, yeah? Imagine that the bridges between the triangles were absent. Then each triangle on its own would just have a set of discrete mechanical resonances. Now you start to couple them with bridges, so the discrete resonances broaden into bands. You have something like a tight binding model, so coupled oscillators. And so that automatically gives you a phononic structure. Okay, so now if I want to write down the Hamiltonian, I will just say that each cell, each unit cell is just a usual optomechanical Hamiltonian with the interaction A dagger A coupling to B plus B dagger. It may be driven by a laser. We will need this to tune the properties of the device. And in addition, though, I will have photons jumping around, for example, here destroying a photon on side J and recreating a photon on side I. And that would happen with a coupling constant J that depends on the geometry and the distance between the defect modes. Okay, so this is what we would call an optomechanical array. And if we now take one step back, we can ask what we got. And it turns out this is a very interesting setting because it has turned into a light tunable metamaterial for photons and phonons. Because as I explained earlier, you can use the laser to tune the effective linearized interaction between photons and phonons. And so you can choose your laser intensity, even as a spatial pattern. You can use your laser phase pattern, even spatially. You choose your laser frequency. Maybe you illuminate with more than one laser beam. And all of this will affect the interaction between the photons and the phonons, in addition to the geometry that you produced. Okay, so now let me highlight one thing that you can use this for, the interaction between light and sound in these optomechanical arrays, namely to produce interesting new phases of the sound waves where the sound wave band structure is considerably altered and also the transport properties of the phonons are considerably changed from what they usually are, with the help of the light field. Okay, so here's first a cartoon of what we want to achieve. Imagine this is a material and we would hit it at one spot. Then obviously a sound wave would propagate more or less spherically into the bulk. However, it would be nice if we could control this better and make the sound wave propagate along a 1D channel. Now this alone you could simply do by deleting all the rest of the material, obviously. But we also want the sound wave to propagate only in one direction, Kairali, as we would call it. And the effect of this is that once the sound wave hits a corner or even an obstruction, it will just continue to propagate in the given direction and will never backscatter simply because it is not allowed to backscatter. Of course, we have to engineer this, but this is the goal. And you can also already imagine that in our case, we want to engineer these peculiar sound wave properties by producing a structure which we illuminate with the right pattern of light. Okay. Now, all of this is connected to the whole field of topological materials. Just briefly, why we are interested in topological properties is very simple, because by definition, they are very robust. They are robust by definition against all the smooth changes that you could apply. So for example, if you have a Möbius strip and you deform it slightly without ever cutting it, it will always remain a Möbius strip and never turn into an ordinary strip. And so some time ago, it was realized that also waves propagating in suitable materials can show topological robustness. This was first understood. The connection to topology was first understood for electron waves in the context of the quantum Hall effect. where it was realized that this quantized conductance that is so useful for applications or metrology really is connected to a topological index that you can calculate. Then it was realized that you don't even necessarily need a magnetic field. A material with spin-orbit interaction is already good enough. And then, of course, people started to inquire, since these things were so exciting for electrons, whether you could also implement them for other kinds of excitations. For example, by now that has been implemented for cold atoms and for photons, and has been at least proposed for magnons. And that is the setting in which we operate. Now, here's a brief crash course to tell you what is so remarkable or what is topological in these structures, regardless of the kind of excitation or wave that you look at. And in order to understand that, it's almost enough to go back to the simplest textbook crystal, which would be obviously a square lattice on which an electron or any particle can hop around. But instead of taking the simplest version of a textbook crystal, you take the second simplest, which is having a unit cell with two sites. So the green and the blue atom or whatever orbital can be occupied by your excitation, which could be an electron or a phonon later or anything. And it can jump around between the different orbitals and propagate in this periodic structure. Now, when I give this talk to optics people or quantum optics people, sometimes I have to explain more about band structures, but of course, since this is more a condensed matter audience, it will be very brief and harmless. So obviously you get Bloch waves, but since you have two orbitals in the unit cell, you also have to give two amplitudes for your excitation to be on either one or the other orbital at any given time. And these amplitudes, in addition, will now depend on the wave vectors. So for different propagation directions and so on, you will get different amplitudes. Now, all of this can be pictorially represented, which in this context is very, very useful. And the way I'm going to represent it is by noticing that obviously you have here something that looks like the wave function of a two-level system, yeah? Like spin up amplitude and spin down amplitude. So I can also represent it in the same way that I represent graphically a spin 1/2, which is namely by a Bloch vector that points into the spin direction. So for each k, I can calculate such a Bloch vector, and then I plot the resulting vector field in the Brillouin zone. Now, the example I'm showing here, most Bloch vectors are more or less pointing down. It's relatively boring. But I claim that if you change the details of the material parameters, the hopping amplitudes specifically that connect the different orbitals, something quite different can happen. And so that happens here. Even without knowing any of the details, you already realize that there is a big, drastic qualitative difference between this picture and that picture. Yeah? Because here it was relatively boring. Here, obviously, something like a vortex, or the experts would say a skyrmion, has appeared in the Brillouin zone. And it turns out that there is no way to smoothly deform this vortex back to the old picture, regardless of what you do. So we have two topologically very distinct situations. Okay, so the mathematicians have a way of quantifying this, and that also has to do with a relation to or can be best explained with a relation to spin 1/2. So if I have any spin system or any quantum system and I adiabatically change the Hamiltonian such that I return to the starting point, for example, I change a magnetic field adiabatically for a spin, and the spin always follows the field and returns to the starting point, I can ask, how does the wave function change? Since you return to the starting point and everything was adiabatic, you expect the wave function to also return to the original value, to the original wave function, with one exception, that is the phase that you accumulate. And the phase has two components. One is just energy times time, that is trivial. But it turns out there is another component, which is the so-called Berry phase, which only in this case depends on the geometry of the path that you follow in parameter space as you adiabatically deform your Hamiltonian. And so in going back to our example, we can now say, look, we have something like a parameter of our Hamiltonian in the Brillouin zone in reciprocal space. The parameter is simply k, the wave vector. So I can ask, how does my wave function, this one, change as I vary k around a closed loop in the Brillouin zone. And again, I will pick up a phase, I will pick up a Berry phase, and I can calculate this Berry phase, and it will have some arbitrary value. If the loop is small, the Berry phase will also be small. However, now I can go one step ahead, and I can add up the Berry phases for all the different little plaquettes into which I have subdivided my Brillouin zone. And at this point, something remarkable happens. If I add up all these Berry phases, it turns out, because the Brillouin zone is periodic, it turns out that the sum of all these Berry phases is an integer multiple of 2 pi. Yeah? And that integer is the so-called Churn number. Here's the way how to calculate it officially, but really you are just adding up all the Berry phases in the Brillouin zone. And because it's an integer, by definition it must be topologically robust. Because if you implement smooth changes that smoothly change your wave functions in the Brillouin zone, most of the time an integer will not change until it does change when it jumps. Okay. So why are we interested in this integer? Well, it turns out that there's a remarkable concept called the bulk boundary correspondence, which is to say these integer numbers that you calculate from the band structure of your bulk system, of your infinitely extended system, they have some very important consequence for what happens at the boundary of your system or at an interface between two different pieces of the material that have different microscopic properties. Imagine, for example, you have one part of the material where you would calculate a Churn number of 0 for a given band, and another part of the material where you would have a Churn number of 1, then you are guaranteed that at the edge between them, you get what is called an edge state. And more than that, you also are guaranteed that this is chiral, so it only propagates excitations into one direction. And now that's very important, because since it is chiral and only propagates in one direction, when you introduce disorder, nothing remarkable will happen. All it can do is to slightly deform this chiral edge state. And that is simply because there is no counterpropagating edge state at this location in the sample. The counterpropagating state is actually somewhere else at the other boundary of the sample, just like in the quantum Hall effect. But locally, there is no counterpropagating edge state, and so you can never backscatter, which is, of course, a very nice feature for application. So this is the main selling point if you believe that at some point we can use topological devices or materials for applications, that you become very robust against backscattering. You don't become robust against, say, absorption or dephasing. Yeah, these are different things, but against backscattering you can be robust. Okay, so now, after this introduction, what about generating topological transport of phonons? And if you could do this, you could really transport sound waves protected against backscattering. You could then go on and look at examples that are similar to what people had done for the quantum Hall effect in electronic physics. And in this case, that would mean to have individual heat reservoirs that are connected by these one-way edge channels that only always propagate heat into one direction. And you could study these, for example, also by reconfiguring the channels on the fly in the same way as you would for a quantum Hall effect sample, use electrode voltages to reconfigure edge states. Okay. Now, when we started in 2014 with this idea, there were basically two prior articles mentioning topology and sound waves together. So one was a work by Kane and Lubensky, where they found that certain particular materials that you could, in principle, construct by connecting masses with stiff joints had zero frequency edge modes that were somehow connected to topology. This is, of course, very different from the sound waves that we want to look at, which are at finite frequencies and really propagate. Then there was another very early speculation in this seminal paper from the field of biophysics, where people looked at microtubules that make up your cell skeleton, and where it was speculated that if these individual microscopic molecules that make up the microtubules would have some magnetic properties, they would give rise to topological edge states at the boundaries of these microtubules. But this is still a speculation so far. For us, of course, the idea would be to exploit the interaction between the light and the sound to engineer these topological structures for phonon transport. And there's one ingredient which I still have to reveal. I already briefly mentioned something has to happen about the hopping amplitudes between the different orbitals. And more precisely, what you need is you need phase factors for these hopping amplitudes. For example, in topological insulators, electronic topological insulators, this is produced by the spin-orbit interaction. Or in the quantum Hall effect, this is produced by the Aronoff-Bohm phase coming from the magnetic field. But obviously for sound waves, it's not so easy to get phase factors when excitations hop around, and we will exploit the light field, obviously. We will exploit the light field to produce this. Okay, so the claim I make here is that the ingredients we need are very, very simple. Namely, you just need a piece of dielectric with the right pattern of holes in the shape of this optomechanical crystal. Plus, you need one laser beam with the right pattern of optical phases. And here is the basic idea, so to speak, the basic unit cell that we want to build on, which can be explained in the following way. Now imagine you have several of these localized phonon modes. They are coupled, so phonons can hop around. For example, they could hop around clockwise or counterclockwise on this triangle. But since the coupling constant that is set by geometry is just real valued, this will in itself not produce anything remarkable. Then there are photons. They are also coupled. But then there is the process that converts phonons into photons. That is the process that we can tune by the laser. Yeah? And as I told you, the amplitude for this process to happen is also influenced by the optical phase of the laser. And that's, of course, where the phase finally comes in, because now we can have a situation where a phonon is first converted into a photon, then the photon jumps, and then the photon is back converted into a phonon. And if the phase for this and that is different at these two sites, then in total I will have picked up a phase. So that's the idea. Yeah? So now a phonon going around this triangle can also interfere with this other pathway and pick up a phase. Now, of course, in order to really get the topological material, it's not enough to build a single triangle. You want to have an extended material. And that is shown here. You want to put these triangles onto a larger lattice, and what you end up with automatically is a so-called CargoMe Letters. So the unit cell is triangular, and these triangles are connected by hopping of photons and phonons. And we want to make sure that at the sites of these optical and phonon modes, we illuminate with a laser, but in such a way that the different sites here are illuminated with different optical phases, and the best choice turns out to be if the phases differ by 120 degrees, because then you get a sense of circulation. So you can say, oh, I'm winding around clockwise with my optical phase. That's important. Just briefly, how to produce this is in principle actually very simple, because if you just take the textbook example of interfering plane waves, and instead of just 2 or 4, you are using 3 at 120 degrees angles, then you will automatically end up with a phase pattern that does the job. So instead of plotting the amplitude, which would just give you an interference pattern here, I'm plotting the optical phase in a color, in a rainbow scale. And what you can see is that there are optical vortices, there are singularities in the phase field, such as this one here. So if you go around this, then the phase winds up by 2 pi in a certain sense of circulation. So this is really an infinite periodic lattice of optical vortices. And so the idea would be then to place the modes that we want to address beneath this lattice that is created by the light waves, and then to extend it into the CargoMe lattice that I already introduced. Okay, so this is a periodic lattice now of photons and phonons. Yes, there was a question. Oh, this is not very critical. I just hand-picked it here, just randomly. The point is that these topological effects, by their nature, are usually very robust. So if I have 0 degrees and then not 120, but 130, and correspondingly the other phase will be less, it doesn't matter. It just has to have an overwhelming sense of circulation in one direction. Yeah. Okay. Now this is a periodic structure of photon and phonon modes, so I can calculate the band structure. And this is what is shown here, frequency versus Kx and Ky. These are 3 photon bands, which really look like the ideal CargoMe lattice bands. And then there are 3 phonon bands, where you already see that band gaps have formed between the individual bands. And the reason for these band gaps is really the coupling between the phonons and the photons. So without that coupling, the band gaps wouldn't be there. Now, having band gaps is the first step towards a topological insulator, but you still need to check whether the bands actually have non-trivial topological properties. It could just be a very standard band structure like you would find in any semiconductor without doing anything special. And so this is what we did. We calculated the Churn numbers for all the 6 bands, 3 photon bands, and plotted this as a function of the experimental knobs you have, which would be the laser frequency and the laser amplitude in this case. And the mere fact that you typically find them not all to be 0 already tells you that you get something topologically non-trivial in these devices. Even with many different phases that here are depicted with different colors, depending on where you tune your parameters. But let's just pick any parameter, and let's ask whether if you now take this material and build a device out of this with boundaries, whether it does the job and really produces these interesting edge states that only go around one way. And so that is shown in this picture. This would be then a finite size sample with a strategically placed defect at the boundary just to show that it works. And your goal is to excite sound waves and to look at which way they propagate. Now it turns out that the optomechanical interaction is also very good just to excite the sound waves. You could use piezoelectric, for example, but you can use the light. And the idea is you have this strong control beam that illuminates the whole structure with this pattern of optical phases that I talked about. So that's a strong control beam that is always on. And then you would use a weak probe beam injected locally at some spot with a different frequency. And now imagine you have 2 optical beams with different frequencies. There will be a beat node between them, which will give rise to a modulated intensity locally. The modulated intensity automatically gives rise to a modulated radiation pressure force. And so you are launching sound waves. You're just wiggling the system locally. And so this is why locally at the spot of the probe beam, you are really launching sound waves. And now you watch them propagate, and you really see that they propagate only in one direction and not in the other direction. So this is a clear sign that you have created this Churn insulator of sound waves using the interaction with the light. Of course, they nicely propagate around all obstacles. Of course, at some point they will decay simply because of the usual decay of dissipation of sound waves. Yeah? So this is not something that you're protected against. It's always the disorder scattering that you are protected against. And then finally, you can even use the light field to image the presence of these sound waves, because it turns out that locally the presence of a mechanical vibration will imprint sidebands on your strong control laser beam. And you can image these sidebands, selecting the frequencies of these sidebands and locally image them. OK. So in principle, you can implement this in any kind of optomechanical platform. But of course, you want to pick a platform where you can produce integrated devices with many unit cells. And so photonic crystals would be the most promising platform. And currently, the biggest challenge still is the disorder in the fabrication. Because at least when Oscar fabricates these devices, he tells me that the geometry is off by about 1%. And 1% of 100 terahertz optical frequency is still 1 terahertz fluctuation of the optical mode frequencies from side to side, which is still too large. And so what they have now started to do is a post-processing technique where they go in and locally change the material, which then allows them to gain 2 orders of magnitude in precision of the alignment of the optical frequencies. And then you can really hope to get the structure working.
So why does this very general robustness argument?
Yeah. So the same would happen in a usual topological insulator for electrons if you were to insert impurity atoms and insert so many of them that basically you're completely changing the material. So the robustness only is valid up to some threshold, and then it breaks down because at some point you don't even have the original material anymore. It's a completely different amorphous material. Yeah.
I have a question about the chirality. So what to do with the light beams? It's polarized? There must be some special polarization.
No.
Right,
No. So this polarization can be fixed. So say it's linear polarization in one direction. What we are looking at was orbital angular momentum, not spin angular momentum of the light field. Yeah.
I wonder if
okay.
you want to have the phonons going in the opposite direction,
Uh-huh.
what would you do?
Ah, so yeah. No, okay. So then you would just change the winding sense for the optical field. Yeah. So the optical vortices would point the other way.
Okay, so this is by locating the beam appropriately or by changing some polarization property?
Oh no, so you have 3 beams and you pick their relative phases. So the 0, 120, 240, and you would just flip 2 of the phases and then that's fine.
Change the edges,
Yes.
optical phase.
Yes. Okay. So when we first proposed this was the first proposal for topologically protected transport of phonons in the solid state. Since then, last year in particular, there have been several macroscopic even implementations of topological devices that, for example, involve coupled pendula or coupled gyroscopes. These are, well, first on the macro scale and then second, all fixed by the geometry. You wire up your pendula in a very clever way, but then you are fixed. Here, of course, we would have a nanostructure and everything is optically tunable. And in addition, you have optical readout as well. And because it's optically tunable, you can even suddenly change the parameters of your system. And for example, you could imagine a quench where you change the parameters such that previously you had some edge state and now you don't have them, or now you have several edge state in a different configuration, and you could watch the non-equilibrium behavior of a topological system when you suddenly quench its properties.
Could you switch the chirality so that you go left instead of right?
Probably, yes.
Yeah, I didn't think of this particular example, but yes, then some of the edge states would have to magically reconfigure to go the other way. Okay, so I want to finish this largest part of my talk by showing you a structure that was produced in the group of Oscar Painter. In principle, this is exactly the device we are seeking. It uses these snowflake crystals to produce localized optical and mechanical modes at these spots. And they are already arranged exactly in the pattern we need, namely in a CargoMe Letters. The only thing that is still missing here is to bring down the disorder to the level that is acceptable in order to see these effects. Okay. And so now in the last 10 minutes of my talk, I wanted to tell you about another topic involving light, but not mechanical excitations, but instead magnons. And that is cavity optomagnonics. We already heard about this in the talk by Nakamura. And in our sense, it's a very exciting topic because, as you will see, there are many, many tight connections to the field of optomechanics. Now, we already had several talks about coupling magnons and microwave cavities, where you would, for example, take such a Higgs sphere with its magnetic excitations and couple it resonantly to the microwave field inside a cavity, possibly even including a qubit. And so then you would study the properties of this coupled system. That is an effort that has been going on in several groups since a few years now. Very recently, however, people also have started to couple to optical radiation at optical frequencies. Of course, with one of the ultimate goals being to be able to do conversion, wavelength conversion between microwaves and optical radiation. And so these are the 2 first experiments in this direction, one in Tokyo by the group of Nakamura, the other at Yale by the group of Hong Tang. And both basically did the same thing, that is sending in light and getting Brion scattering of light that is able to excite a magnon in the process. Okay. Now, I want to point out a very important difference between these 2 examples of coupling magnons to the radiation field. If we are in the microwave regime, then the coupling can be resonant. So the relevant Hamiltonian would couple just some spin component to the amplitude of the radiation field. The frequencies need to match, but of course this is possible because you have the typical gigahertz frequencies in the magnon modes. then it's really a model of coupling a large spin to the radiation field. And of course, the coupling is fixed. The coupling is set by the geometry and the details. In contrast, if you go to the optical regime, what you get and what you also need is parametric coupling, because the frequencies do not match at all. So what you have is the spin couples not to the amplitude, but to the intensity of the field. Because of that, the frequencies can now become completely arbitrary. They don't need to match anymore. It's only the fluctuations of the intensity whose frequency scales have to match the magnon. And because of this Hamiltonian, it is very obvious that there is a direct analogy to optomechanics. You only have replaced the mechanical displacement by a spin component. So there's a very fine analogy. And in addition, just as for optomechanics, if you now were to linearize the interaction by introducing a large amplitude alpha and doing the same tricks that we did before, you would also in this case arrive at a tunable coupling instead of a fixed coupling. So this is the parametric coupling that I want to talk about. Now the way to visualize this is the following. Let's pick the most elementary Hamiltonian of the sort, which would include an optical mode, which would include a spin that here is aligned along the z direction and is precessing if it does not point directly into z. And then you would have the coupling to the light intensity. And so what this coupling means is that depending on the spin projection, for example, along the x-axis, you are shifting the optical frequency of your optical cavity up and down in the same way that in the optomechanical case, your mechanical displacement shifts the optical frequency up and down. And so now you imagine you have your collective macro spin precessing around, and this will give rise to shifts of the optical frequency. Now, a few brief words about the derivation of the Hamiltonian. If you consider a very simple system of non-interacting spins, such as you would have, for example, in a paramagnetic spin ensemble or in a cloud of cold atoms, then there's practically only two lines to write down this coupling Hamiltonian. And for example, this was discussed at length by Brahms and Stamper-Kern in the context of cold atoms. Here, of course, we have something physically different, namely a rigid, spatially extended Magnon modes, which is very well separated in frequency from all the other modes, and that's important for applications. The coupling effect in all the cases is the same, namely the Faraday effect. So if you send in a light beam through a magnetized sample, you can get a rotation of the plane of polarization. And the rotation angle per length then defines your microscopic coupling strength, here called F. So on the microscopic level, the interaction Hamiltonian would be written down like this, with the coupling strength times an integral over all of space that couples the magnetization density to the optical spin density. So E star cross E tells you in which direction is your wave circularly polarized. And for best effect, that should match the direction of the magnetization to which you want to couple. Okay, now if you want to go to a smaller structure where you have localized optical modes, then of course this turns into a Hamiltonian such as this, where you couple the spin to either the intensity of the optical modes, so the photon number, or even transitions between different optical modes. And there's still one word of caution here. In order to get at such a Hamiltonian, what you need is that either that you decompose this magnetization density into a couple of Magnon modes, but that requires that you are still in the regime where you can talk about small Magnon excitations, so small Magnon numbers. Or if you want to go to larger excitations, it's best to imagine you are coupling only to the one interesting homogeneous Magnon mode, the so-called Keitel mode, where you can then imagine to have, in principle, arbitrary excitations of the spin. And so the coupling strengths obviously depend on overlap integrals. Just one simple example here. If you imagine you have two optical modes that are circularly polarized, left and right, then the coupling would look like this, where you couple the spin pointing into the direction of the circular polarization axis, shifting the left and the right circularly polarized mode with a different sign, obviously. You're seeing a different refractive index depending on the magnetization for the two circular polarizations. And so the material constant enters in the way that you have this coupling G multiplied with S, and that would turn out to be on the order of 10 to the 10 hertz for the case of YIG, for example. Now, coming back to the Hamiltonian, which I showed before, you arrive really at a system that is very, very conceptually similar to optomechanics, coupling a Magnon mode to an optical mode with some coupling strength. And in particular, if you allow yourself to be in the limit of small excitations, where your spin only deviates a little bit from the North Pole, then you can treat it in the usual way as a harmonic oscillator. For example, think of the Eugene-Polzig experiments for cold atoms where the same is done. And then you really get the optomechanical Hamiltonian with all the associated effects. Just a brief word about the coupling strength. The bare coupling, which you write down in this way, G0 times A dagger A, the photon number, times B plus B dagger, which are the Magnon operators. The bare coupling strength could be as large as, say, 0.1 megahertz if you were able to reduce the size of the mode volume down to 1 micron. So this is, of course, the minimum size that you could have. And then these coupling strengths really become comparable in principle to what Oscar Painter can do for his optomechanical crystals. So that is an exciting outlook. Of course, right now the volumes are still much, much larger with these millimeter scale YIG spheres. So one of the reasons we are excited about this is obviously that now you can translate the whole table that I was showing you before and always replace mechanics by magnonics, replace optical spring effect by an effective optical induced magnetic field, and so on. And in principle, you can try to go through this whole table, but with a different physical system, also, of course, with different parameters. In addition, however, you can also try to go beyond optomechanics. You don't need to stay in this regime where you can approximate the Hamiltonian such that it becomes virtually indistinguishable from the optomechanical Hamiltonian. Instead, for example, you could go to larger excursions of the spin on your Bloch sphere, then you really feel that it's a spin and not a harmonic oscillator. Or you could even consider more interesting spatial patterns of the magnetization, for example, vortices or skyrmions in your magnet. Okay, and so this is what we looked at very recently. We wanted to find out the effective spin dynamics on this Bloch sphere under the presence of the laser-driven optical cavity and the optomagnetic interaction. And what you find is you get an effective evolution equation for the spin that now includes a magnetic field that has a component that is determined by the interaction with the optics, and also includes an effective damping, similar to Gilbert damping, that again is determined by the interaction with the optics. And both of them depend nonlinearly on the detuning and on where you are on the Bloch sphere. So here, for example, you would then see if I'm in this blue region, for example, instead of damping, I get anti-damping. If I'm in the red region, I get the opposite effect, I get true damping. And what can happen then is you evolve to limit cycles for the spin that are produced by the optical field, by the interaction with the optical field. And so you can have simple limit cycles, or you can have period doubling, and finally you end up in a chaotic regime. And then you can even try to go through such a bifurcation diagram in principle in order to know what the spin does. Okay, so this brings me to my summary. In the first longer part, I hope I showed you that with these optomechanical arrays, you could really do great experiments where you use the light-sound interaction to, for example, engineer the properties of the sound waves. And then in the second shorter part, I told you something about this exciting new area of cavity optomagnonics. Okay, thank you.
This physics in real systems, for example, using the electron interaction to create non-trivial topological Phonon phases?
In principle, of course, yes. Because there's an interesting and tight connection between the optomechanical Hamiltonian and Hamiltonians that are known in electron-phonon physics. For example, for the array, what I showed, if you show this Hamiltonian to someone from condensed matter theory and you don't reveal that the A operators refer to photons, it would be the so-called Hubbard-Holstein model, where electrons instead of photons couple to localized optical phonons. So in principle, probably yes. I don't know what the real translation of this would mean, whether the optical vortices correspond to electronic persistent currents that are flowing in a circle, possibly. It may be a little bit more difficult because photons are bosons, so I can put all of them in the same mode. That is the good mode that does what I want. Electrons, as we know, are fermions. It's a little bit harder because sometimes only the fermions around the Fermi energy count, and these would only be a few. That is just my first guess.
And let's say superconductors.
Yes, in principle, yes. There I don't know how if... Okay, then you have to ask exactly what you want to do. Of course, everything I talked about here can be implemented in the microwave optomechanical world, where I have lumped element LC oscillators made of superconducting material, and then I play the same game. That is in principle possible. If you want to talk to the more... But these, of course, are artificially produced large phonons, so to speak, of a vibrating capacitor. If you want to go to the microscopic phonons, well, then probably you have to think again.
Yes, please. So regarding the controlled propagation directions for phonons, is there some prospect to implement this in refrigerator or heat engine type of devices?
Maybe, I don't know. I usually get the question, doesn't that violate the second law and so on? You have to realize that when I show these different heat reservoirs that are connected by the one-way streets, by necessity, since these one-way streets run around the boundary, they will close up on themselves. So you will not, for example, by connecting two heat reservoirs of equal temperature, suddenly cool the one and heat the other, because there will be another stream of heat coming around the boundary of the sample, and so everything is fine in equilibrium. Yeah? But whether it can be used for a clever heat engine or something, I don't know. Would be interesting to think about this.
Yes, please.
Pushing the analogy between phonons and magnons, can you control the topological band structure of magnons by lasers? Is it
Oh yeah, so in principle, of course, in the field of spintronics, people talk about controlling also the band structure of magnons. Even people have thought about connecting to the first part of the talk, magnonic Churn insulators and topological insulators. Now for these devices, of course, you want to have material with good optical properties, such as YIG. And at least so far, it seems not entirely trivial to do with YIG the same things that people do with silicon or aluminum nitride to produce these nice photonic crystals. Yeah? So that's a little bit the bottleneck at the moment.
Any other question? Yes, please.
I have a general question. There are some proposals to make topological crystals of light.
Yes.
And so there can comment how the perspectives do the same thing with phonons. What kind of materials or structures would be interesting? So we are using here light combined with
You are now wanting to talk, so the typical proposals for photonic topological insulators simply use the geometry. By that way, of course, they are also fixed somehow in their properties. For example, you can try to couple disk resonators where the light already runs around in one winding sense of circulation and then couple them in an interesting way so that the phase accumulated in one direction is different from the phase in the other direction, and such samples have been produced. In principle, you could then also do the same for phonons if you have whispering gallery mode for phonons in such disks. But this is probably not the smartest way to do it. Actually, before I introduced the cavity optomagnonics part, I had another part of this talk that was talking about a purely phononic device based on the snowflake crystal, actually, that purely by the geometry would enable you to produce artificial magnetic fields for the phonons and then observe edge states. So then it's purely by the geometry. Of course, it's fixed. It's not as flexible as this one, but you don't need the light field.
Right. One question on the first part. So in essence, this was kind of single particle physics, right? So I think it would be interesting to add interactions with a qubit or something.
Okay. So we hadn't even thought about interactions with a qubit, which would probably mean basically you're going for the microwave optomechanics platform, and then you can more easily add a qubit. I know that people are starting both in the microwave and photonic domain to imagine, okay, if I have a photon state going only one way, what would happen if the qubit here leaves its excitation and it only travels one way? So yeah, so we haven't thought about the qubit part yet. It could be an interesting idea.
Any other question? Okay, so then let's start